students, welcome to Solid State Physics, lecture number 10. I'm Dr. Pervaiz Ahmad. In this lecture, we are going to discuss about the cubic crystal system. So let's proceed towards today's lecture, that is about cubic crystal system. The first type that we have is about sample cubic system. So in a sample cubic system, we have one lattice point, so it is called the primitive unit cell. So just like you can see it here, in the unit cell, the atom at the corner are cut because only a portions, that is 1/8 belong to that cell. The rest of the atom belongs to the neighboring cell. So coordination number for the sample cube is equal to 6. So here you can see the formation of a sample cubic system and how, just like we mentioned that the atom at the corner, it is not only belong to that particular lattice point but also to the nearest neighbor, and how it constitute the crystal. So you can see the animation by yourself, that how the crystal is being the whole crystal is being constituted from the sample cubic system. The atomic packing factor of sample cubic, you can see it here, it's equal to 0.52 for a sample cubic. And how we do the calculation, just like we have mentioned, the atomic packing factor is equal to the atom per unit cell divided by the volume per unit cell. So you just do the putting, you just put the values, and we get the values for the atomic packing factor for sample cubic, which is equal to 0.52 for the sample cubic system. The second type we have in the cubic crystal system is called body center cubic. In this body center cubic has two lattice point. So BCC is non-primitive cell because it do not have one lattice point for a unit cell. So along with the corner, it also has an atom or a lattice point at the middle. So that's why we cannot call it as a primitive unit cell. So it is included in non-primitive unit cell. And we remember BCC has 8 nearest neighbor, and each atom is in contact with its neighbor only along the body diagonal directions. That you can see it here. The one that we are saying about diagonal direction, so that you can see it here in this figure. So many metals like iron, lithium, sodium, etc., including the alkali and several transition elements, choose the BCC structures. These are the type of the BCC structures. The famous type of the BCC structure include that of iron, lithium, sodium, and some of the alkali metals. They all constitute the BCC structures. The atomic packing factor of BCC, that I mentioned, that the volume of the atom divided by the volume of the unit cell is equal to 0.68. And how we do the calculations, so here you can see the detail by yourself. You just do the sample mathematics. You people have studied in some of your basic classes. So you just put the values, that is atom per unit cell divided by the volume for divided by the unit cell. You just put the values, do the sample calculation, and you come to the point, that is atomic packing factor. The third type that we have in the cubic crystal system is face center cubic, or FCC. So in FCC, there are atoms at the corners of the unit cell and at the center of each face. We have atoms not only at the corner but also at the center of each face of the cubic system. That's why it is called face center cubic system. We have atom at the center of the face. So that's why, just because of that, we call that phase center cubic system. So in phase center cubic, we have four atom. I mean, it has four atoms, so it's a non-primitive cell again. Four atom per unit cell. So it's also a non-primitive cell. So what are the example of the FCC? So there are many metal like copper, nickel, lead, etc. that crystallizes in FCC structures. I mean, the example, the famous FCC structure included copper, nickel, and lead, etc. They all constitute the phase center cubic crystal system. So here is an example. I mean, again, you can see the animation by yourself, that along with the corner, here you can see each phase. I mean, it has the atom, I mean, that is point at the center of the each phase, and how they are being connected with the diagonals, I mean, to the other atom. I mean, the phase center atoms, how it's connected to the nearest neighbor. So this animation you can clearly observe it. So how we do the calculation of atomic packing factor of FCC? So again, here the formula is the same. The only thing you should worry about is, once you calculated the atom per unit cell, so the volume for atoms, I mean, for the volume of the atom, you should worry about the value of the radius, that is R. So here you can do the calculations from the structure. I mean, here the calculation, if you have a knowledge of basic mathematics, so with the help of that you can easily find out the value of R, and then you should put it here, and after that doing the sample mathematics, so you can find the value of atomic packing factor for the FCC, not only for the FCC but for the sample cubic and also for the body center cubic. But you should know a little about, you should have basic knowledge of the geometry and basic knowledge of the mathematics. So with the help of that you can easily calculate the atomic packing factor of each cubic crystal system. So unit cell content, counting the number of the atoms within the unit cell. So how we do that? So for that we have a table. Inside that table, just like you can see, first we have atoms, type of the atoms, where the atom are being placed, shared between, the atoms are being shared by how many cells, and each atom counts, if the atom is placed at the corner, that so what portion of that atom is being counted. So if the atom is at the corner, so it's been shared between the 8 cells. If you have atoms at the corner, so they are being shared among the 8 cell, and each atoms count only 1 by 8. So if we have atom at the phase center, so phase center atom is shared between the 2 cells, and each atom counts only 1 by 2. If the atom lies the body center, so it's been shared between 1 cell, and each atom counts 1. And if we have edge center, so edge center atom, it's been shared between the 2 cell, and each atom counts 1 by 2. So what is the connection between the lattice type and cell content? So if the lattice type is sample, so for sample we have cell count equal to 1, and that you know why it's 1, because we have 8 multiplied by 1 over 8, so that is equal to 1. For the body center, cell count is equal to 2, and you know that why it's 2, because we have the calculation, along with the corner atom we also have an atom inside the body, in the center of the body. So from this calculation you can easily understand that why we have 2 cell content. For the phase center we have 4 cell content, and that you can check, you can do the calculation, That's why we have, we have 6 bases, and each bases we have 1 by 2, and along with that we have the atom at the corner, and each corner contain 1 over 8. So with this sample calculation you can you easily understand that why we have 4 cell content. And for side center we have again 2 cell content, and that again you can do the calculation. We have two sides up and down. So at the corner again you can see in sample cubic we have 1 over 8 of the atom, and we have 8 corner, so is equal to 1. And then we have uh, top and bottom side, so that these are the two sides, so each side contain 1 by 2, so the total content is equal to 2. So example of atomic packing factor. So you should remember that it is very easy to show that filling of the space by spare is 74%. For example, for the FCC unit cell of cubic close packing, that we call CCP, with an ABC with the ABC layer refit, for the sphere of radius r touching along the face diagonal that you can see it here, the cubic unit cell parameter is calculated as x is equal to 2 under root r. So the total unit cell volume is equal to x cube. So that is equal to 16 under root 2 r cube. So the aquifer volume is equal to 4 sphere, that is equal to 16 phi r cube divided by 3. So space filling is equal to 5 over 3 under root 2. So that if you do the calculation, so that is equal to 74.05%. So that exactly what we have already mentioned, that is equal to 74%. So that's all we have for this lecture. Thanks for watching. Stay tuned for the next lecture, that will be about hexagonal triclinic and monoclinic system. Till then, bye bye.